Electric power. The electrical work is given by the unit of joules. The electrical work is the transfer of charge, which is Q, through a potential distance or potential difference. This is given by the illustration. If there is a charge Q and the Q is energized to move from one point to another point, the difference between 2 points is called a potential difference. The electrical work can be calculated by the formula, which is W is equal to Q times V, where W is the work in joules and charge in coulombs is the Q, while the potential difference in volts is the V. Electrical power. Electrical power unit is in watts. Electrical power is the electrical work in joules per unit time in seconds. That is also equal to work over time. So, the formula for electrical power is equal to V times Q, since that is the formula for work divided by time. However, Q over T is also equal to I, because I is current. And therefore, if we replace Q over T with I, the new formula will be P is equal to V times I. So, P is the electrical power in watts, V is the potential difference in volts, and I is the current in ampere. So in this problem, we are going to compute for the work and the average power that is required to transfer a 96,000 coulomb of charge, 96K or 96,000 coulomb of charge within 1 hour through a potential rise or potential difference of 50 volts. In other words, if we have a charge that is 96 kilocoulomb or 96,000 coulombs, we'll let that charge, energize that charge, and transfer that charge from one point to another in the potential difference of 50 volts within 1 hour. What will be the work and what will be its power? We are going to apply the formula. W is equal to work, which is equal to the charge times the potential difference. The charge is 96,000 coulombs or 96 kilocoulomb multiplied by the voltage, which is 50 volts. The work is equal to 4.8 times 10 to the positive 6 joules. In other words, that is also equal to 4.8 megajoules. So that will be the computation for work. Now we are asked also to compute for power, and power is equal to W over T, or the work done over time, which is equal to the work is 4.8 times 10 raised to the power of 6 joules divided by the time, which is 1 hour, and that is also equal to 3,600 seconds, and that will be equal to 1.3 kilowatts, also which is equal to 1,300 watts. Here we have another example. We have a bulb that is equal to 60 watts, and 60 watts is already the power. This bulb is attached to a voltage source which is equal to 120 volts. Therefore, the question is, how much current does a 60-watt light bulb draw when connected to its proper voltage, which is 120 volts? From the formula, power is equal to voltage times current. In order to solve for current, we are going to transpose the formula from P is equal to V times I to I, which is now equal to P over V. Since P is the power and V is the voltage, we can substitute the values directly. So I is now equal to P, which is 60 watts, and V is equal to 120 volts. Therefore, I is equal to 60 watts over 120 volts, and the answer is 0.50 amperes. Therefore, I is equal to 0.50 ampere. The resistor. The concept of resistor in terms of current, voltage, and power is this. A resistor resists the flow of current, and so it is also equated to power loss. And so how can we calculate power loss in a resistor? We can still make use of the previous formula, because the previous formula for power is equated to the voltage times the current. However, in this context, it is a power loss. And so, we are going to replace, according to Ohm's law, voltage is equal to I times R. So that, from the original formula, power is equal to voltage times R. Replacing now voltage with IR, there will be two I's, which is I times R. And so, that is also equal to I squared times R. And supposing if I will equate I squared with the Ohm's law again, that will also be equal to V squared over R squared. Multiplying to R, we can cancel out R over R squared. And so, power is also equal to V squared over R. So that our formula for power loss is equal to either making use of I squared times R or V squared over R. And so, potential difference, which is squared, over the resistance, which is ohms, is actually how we can calculate power loss in a resistor. Or, we can also calculate power loss in a resistor using I squared times R. The thermal energy generated in a resistor is actually the power loss in a resistor. As power is lost in a resistor from the action of resisting the flow of current, will actually generate thermal energy, and thermal energy is equated to power loss. Therefore, we are still going to make use of the same formula, which is P is equal to I squared times R, or V times I, which is also equal to V squared over R. So in this problem, we have an electric iron. The electric iron is about 20 ohms. The resistance is 20 ohms, and it is taking a current from a source which is 5 amperes. So the question is, what will be the thermal energy in joules if it is running in 30 seconds? So the first thing that we have to understand is that we are asked for the thermal energy, and thermal energy is actually the work done in joules. So now we have the formula for power, and power is equal to work or energy. So in this case, the thermal energy divided by time. And so if we would like to get for the value for the thermal energy, we can just transpose the formula as energy is equal to power times the time. And so we are going to rewrite that. Energy is equal to the formula for getting power of the relationship between resistance and current is that I squared times R is actually the power. Multiply that by time, which is 30 seconds, and so we get 5 amperes raised to the power of 2 times 20 ohms times 30 seconds, and the energy or the thermal energy that is produced by the electric iron is actually 15 kilojoules. Here are some conversion units of energy and power that you need to understand. 1 watt is equal to 1 joule per second. That is also equal to 0.239 calories per second, or equivalent to 0.738 foot-pound per second. And 1 kilowatt is equal to 1.341 horsepower, or which is equal to 56.9 British thermal unit per minute. And 1 horsepower is equivalent to 746 watts, or equivalent to 33,000 foot-pound per minute, which is also equal to 42.4 British thermal unit per minute. And 1 kilowatt hour is equal to 3.6 times 10 raised to the power of 6 joules, or 3.6 megajoules.